Stability is a fundamental concept in the understanding of the behavior of dynamical systems. Systems often have fixed points or equilibrium points. Take, for example, this pendulum. If we place the pendulum in the downward position, it will just stay there, remain fixed. The stability, or lack thereof, of these equilibria determines whether or not the system will return to this equilibrium point after perturbations. In applications, equilibrium points or trajectories often correspond to the desired behavior of a physical system. For example, the behavior of an aircraft at cruising altitude. Since physical systems are always subject to perturbations and disturbances, understanding the stability of these equilibria is then of fundamental importance to ensure that the engineered system behaves as desired. As an added bonus, by mastering the concept of stability, we can often improve the stability properties of equilibrium points, or even make points that were previously unstable stable. In today's video, we're going to go on a whistle-stop tour of one of the most fundamental stability tools, Lyapunov's stability criterion. By the end, my hope is that you'll have some appreciation of the maths that underpins this result, and along the way we'll also get to revisit some curious results from combinatorics and topology. To support us on our journey, we first need to introduce a mathematical language to describe how dynamical systems evolve over time. We're going to use discrete time state space models. These models consist of two main pieces, a function and a vector. The vector is typically referred to as the system state. This is a set of variables that sort of captures the list of things that you would need to know about the current configuration of your system in order to be able to predict where it would be next. For example, when modelling our swinging pendulum, we might choose for our state the angular velocity and angular position of the pendulum. The function then just describes how these variables interplay with the parameters of the system to make a prediction about where it will be at the next point in time.
If the state's got dimension 2, we can sort of easily imagine this in terms of points jumping around on a set of axes. Suppose we were at this particular point here in our state space with x1 coordinate given by this value and x2 by this value. And suppose also that if we take this vector and we put it into our function, we get this vector out. Well, all our state space model is saying is that if we start here, one point of time into the future, we're going to be here. So this point would be moved from this point to this point. And the state space model is just specifying this one time look-ahead map for every single point in our state space. So perhaps our state space model says that this point here is mapped here, and this point here is mapped here. And the state space model tells us how to do this for every single point. Now we can use this to build up trajectories of our system. So if we want to know where we would be 2 time steps into the future, well, we know after 1 time step we'll be here. And we know that this point gets mapped here, so after 2 time steps, this point will be mapped down here. And by sort of iterating this process, we can look further and further into the future or build up longer and longer trajectories for our system. So suppose this point gets mapped here, and this point gets mapped here, and so on. We could do this for as long as we wanted. In amongst the sort of chaos of points jumping around our state space, there are a few special points that remain fixed. And these are called equilibrium points. Let's suppose that this point here at the origin is an equilibrium point. Well, what does that mean? Well, this is just a special point where if we take this vector, put it into our state space model, we get the same vector out. So if we start here, we stay here. And that's what it means to be an equilibrium point or fixed point.
Before moving on to discuss stability of equilibria in the context of state space models, we're going to take a brief detour to discuss Brouwer's fixed point theorem. We're actually going to quickly talk through how you can arrive at Brouwer's fixed point theorem from a result from combinatorics called Sperner's lemma. Sperner's lemma is all about colouring in vertices on triangles. Suppose we have a triangle that we've split up into smaller triangles, and we've coloured the vertices such that each corner of the big triangle has a different colour. And more than that, the vertices along the edges of the big triangle are coloured with either of the colours at either end of the edge. So in this example, our 3 corner colours are green, blue and red, and so the remaining vertex on the left edge of the big triangle could have been coloured green or blue. Similarly, the one on the right could have been coloured blue or red, and the one on the bottom green or red. Sperner's lemma then guarantees that no matter how we do this colouring, as long as we follow these rules, there's guaranteed to be at least one small triangle that has one vertex of each of the 3 colours. Remarkably, the same thing continues to hold even as we add more and more small triangles. We have to keep colouring in the edges of the big triangle according to the same rules. But any of the vertices sort of in the centre of the big triangle can be coloured in using any of the three colours. No matter how many of these small triangles we add in, Sperner's lemma guarantees that at least one of them will have vertices with three different colours. What on earth has this got to do with fixed points, I hear you ask? To see, suppose we have some function g that continuously maps points on the big triangle to other points on the big triangle. To help keep track of things, we've introduced some coordinates q1, q2, q3. The points on the big triangle then correspond to the vectors q, for which each of the components are positive, and q1 plus q2 plus q3 is equal to some constant. Our goal is now to determine whether this function g has a fixed point or equilibrium point, that is, a vector q such that if we put it into the function g, we get the same vector out. We're now going to deduce that g must have a fixed point using Sperner's lemma by colouring in points on the big triangle according to the following three rules. To apply these rules, we first take any input point on the big triangle q and apply our function g to get another output point on the big triangle q+. We then compare the first coordinates of the input and output points. If the first coordinate has decreased in value, we colour in the point green. If instead the first coordinate doesn't decrease, but the second coordinate does, we colour in the point red. Finally, if only the third coordinate decreases, we colour in the point blue. Note that since the sums of the coordinates on the big triangle is equal to some constant value, if none of the three coordinates decreases, then q plus must be equal to q, and we'll have found a fixed point by pure dumb luck. The reasoning here is that because this sum is constant, if any coordinate strictly increased, then another must strictly decrease, and so one of our three conditions would have been triggered. So the only remaining option is that all three remain the same. Let's now start colouring in points on a triangulation of our big triangle, starting with the bottom left corner. Since this input point has q2 value equal to 0 and q3 value equal to 0, and our function g maps points on the big triangle back onto the big triangle, our only options are either that the q1 coordinate decreases, in which case we would colour it in green, or we found a fixed point. Assuming that we haven't been outrageously lucky, let's colour it in green. We can similarly colour in the other two corners blue and red. How about the other points along the edges of the big triangle? Let's start with the bottom one. This point has q3 value equal to 0, so we can't colour it blue. Green and red are options, though. The other points on the edges of the big triangle can also be coloured in with either of the colours at either end of the edge. Putting this all together, we realise that in the process of colouring in the points on our triangulation, we have either found a fixed point or we've coloured things in according to our set of rules from before. Therefore, if we haven't found a fixed point, we can at least be sure we found a triangle with one vertex of each colour. In fact, no matter how finely we triangulate our big triangle, Sperner's lemma guarantees we'll find one of these special small triangles. We're now just a whisker away from demonstrating that G has a fixed point and proving Brouwer's fixed point theorem. In essence, what we've been able to show through this process is that either we'll find a fixed point or be able to produce an infinitely long sequence of ever smaller triangles. Let's draw one of each size onto our big triangle. Since our sequence is infinitely long, one sub-triangle of the big triangle must also contain an infinite sequence of ever smaller triangles. Let's say it's this one. Similarly, this triangle must also contain a sub-triangle containing infinitely many elements from our sequence. By repeating this process, we can be certain that our infinite sequence of ever smaller triangles contains a subsequence in which the triangles are converging towards a point. Recalling now that each of our triangles has one green vertex, one red vertex, and one blue vertex, we realise that we've identified three sequences of points, all of which are converging to the same point. Along our first sequence corresponding to the green corners of the triangles, our first coordinate is always decreasing. Along the second sequence corresponding to the red corners, the q2 coordinate is decreasing, and along the third, the q3 coordinate is decreasing. It then follows that since G is continuous, and every point on the big triangle has q1 plus q2 plus q3 equal to constant, that the point these sequences are converging towards must be a fixed point. And there we have it. Any function that continuously maps points from a triangle back onto the triangle must have a fixed point. And from Sperner's lemma arises Brouwer's fixed point theorem. In a little bit, we'll illustrate how to use Brouwer's fixed-point theorem to demonstrate the existence of Lyapunov functions for simple state space models. But first we need to talk a little bit more about equilibrium points and introduce the Lyapunov stability criterion.
And the notion of stability is just trying to capture what happens along trajectories around that equilibrium point. So if we start over here and we follow a trajectory, is it heading towards our equilibrium point? Will it get there eventually? Or will it sort of always stay a certain distance away? Or will it get further away? These are the sort of the ideas that stability is trying to capture. And Lyapunov functions just offer a kind of convenient way to describe this process of getting closer to or further away from an equilibrium point mathematically. And they're based on what are called Lyapunov candidate functions, and these are just sort of special functions that satisfy a few properties. And the first thing that you need to do to be called a Lyapunov candidate is you have to assign a number to every single point in the state space. And more than that, you have to assign the number 0 to the equilibrium point. So if we evaluate our Lyapunov candidate at the value in our state space equal to our equilibrium point, it gives the number 0. How about all the other points? Well, it gives them some positive number. And if you're a function that satisfies that, you're a Lyapunov candidate. How can we use this to sort of capture the ideas of stability or instability? Well, perhaps it's best to just build things up from an example. So suppose we have such a Lyapunov candidate. Well, we know our Lyapunov candidate is equal to 0 at our equilibrium point. How about the values where it's equal to 1? Suppose for our particular choice, every point along this curve has got Lyapunov candidate value equal to 1. So this is a contour of v of x is equal to 1. If I take any point along this curve and put it into this function, I get the number 1. How about the number 2? Let's suppose it looks like this. This is our contour of Lyapunov candidate equal to 2. And we could imagine doing this for sort of any contour. And the value is 0 here, so perhaps it's most helpful to imagine the contour sort of getting bigger and bigger and bigger with ever larger values of Lyapunov candidate. So how can we use this to capture our idea of stability? Well, we do it by looking at how the value of our candidate changes along the trajectories of our system. So here we see that we started on a contour of value equal to 2, and one step into the future, we ended up on a contour of value equal to 1. And suppose we were very careful about how we picked our Lyapunov candidate, and suppose that this point here was also mapped to a level of lower Lyapunov candidate. And the same was true of this point here, and in fact it was true of every single point everywhere in the state space. So if we were to write that condition down, what would it mean? It would mean that the value of our Lyapunov candidate, when we look one step into the future, is less than the value of our candidate where we were evaluated before. And if you satisfy this condition, you're called a Lyapunov function. And this is actually capturing exactly our idea of stability. So why so? Well, this implies that suppose we have some value of our function at an initial point on a trajectory. Well, this condition guarantees that one step into the future, the value of our Lyapunov function will have gone down. So one step into the future, we're at a lower level. And then the step after that, we're also at a lower level. And so on, and so on, and so on. And since the equilibrium point is the only point that's been assigned value 0, this means that along every single trajectory, we must eventually be tending towards our equilibrium point. So this is why we would, this is how we would demonstrate an equilibrium point is stable using a Lyapunov function.
How on earth are you supposed to find a Lyapunov function?
A natural thing to do at this point might be to ask an expert. We know that we're searching for a function within this particular class of candidate Lyapunov functions, and our objective is to find one that meets this stability condition. So we know what we're looking for. Let's ask an expert what they would do. Unfortunately, the answer that you get would probably depend very much on the type of expert that you asked. For example, if you asked a physicist, I have no doubt they would respond very enthusiastically that this Lyapunov thing that you're asking for is nothing but an energy function. And as long as our dynamical model is a model of something reasonable, we can use the laws of physics to deduce our Lyapunov function with no effort whatsoever. If we asked an expert in optimization, they would probably nod sagely and declare that our class of Lyapunov candidates is a very amenable class to the methods of optimization. I will show you how to parameterize this class in a suitable way, and then we will use the tools of convex optimization to determine one that meets your stability criterion. If you asked a control system engineer like me, you'd probably smile and say, it's a good thought, but I think you're actually asking the wrong question. Why would you want to find a Lyapunov function? Surely it would be much better to just write down the Lyapunov function that we wanted, and we could then design a control system to modify our dynamical model so that it meets our stability criterion. At the end of all of this, you might then be forced to go and ask a mathematician. Unfortunately, this won't get you very far. They'll just sort of blink at you in a confused manner and ask why on earth you would want to find the Lyapunov function. Surely a simple demonstration of existence would suffice. At the end of all of this, frustrated, you probably realize you're going to have to figure it out for yourself.
So that's exactly what we're going to do with the rest of our time together. We're going to try to build our intuition for simple Lyapunov functions and try to understand what classes of state space model they can be used on. We're going to start our journey with this simple Lyapunov candidate. We have to start somewhere, and surely at least our physicist friend would be happy with this. Lots of energy terms like kinetic energy or the potential energy stored on a capacitor have squares in them. Drawing this function out with Grant's fancy software, we see this particular Lyapunov candidate looks like a bowl and the level curves are circles. This Lyapunov candidate will in fact work for some simple state space models, but it's fairly easy to construct some for which it won't. For example, it won't work if our state space model contains the following trajectory. This system appears to be stable, but we can't verify its stability using this candidate because after the first step of our iteration, we've moved to a higher level of Lyapunov candidate. Rather than just abandoning this idea and declaring our physicist friend a fool, let's try to think how we can modify things. It seems as if we could only squish and rotate these circles, we might be able to come up with something that worked, at least for this trajectory. In order to squish and stretch and rotate our circles, all we need to do is introduce a linear transformation. So rather than using a Lyapunov candidate given by the dot product of the system state with itself, let's first take a linear transformation of the state using a matrix S and then take the dot product. This sorts out this trajectory nicely and indeed seems to work when we look at others as well. Generating functions in this way produces a really rather rich class of Lyapunov candidates. By choosing different matrices S, we're able to produce all sorts of ellipses with different rotations and levels of squishedness. Something rather interesting happens when we push this to the extreme, in which our ellipses collapse to straight lines. The function we get is actually not a valid Lyapunov candidate because the equilibrium point isn't the only point with zero value. However, we can
just twist the same idea slightly to capture the idea of instability. So if we just turn this condition around, so if instead we could find a Lyapunov candidate such that its value, one point of time into the future, was always at least as big as the value where it started, well then we would be able to conclude instability. So just imagine that we were on this contour. If we have this condition, it would imply that we'd move to another contour that had Lyapunov value at least as large, and we would never get down to our equilibrium point, which is the point with zero value. And in fact, we can sort of bend things slightly. We don't need our equilibrium point to be the only point with zero value when demonstrating instability. It's fine to use greater than or equal to zero, as long as there are some points which have Lyapunov function value bigger than zero.
Now we have some idea of how to demonstrate stability or instability using Lyapunov functions, and also have identified a useful class of Lyapunov candidates. Let's try to nail down a method for finding a suitable Lyapunov function for a given state space model. We're only actually going to cover the special case when the state space model is linear. However, the ideas that underpin the approach we're taking work in far greater generality. Let's start by trying to find a more efficient and descriptive way to describe our class of Lyapunov candidates. Every Lyapunov candidate generated by a linear transformation S can be equivalently described through a matrix with entries P1, P2, and P3. This means that we can represent any of our Lyapunov candidates with a point in 3D space. For example, this point corresponds to the Lyapunov candidate with level curves illustrated on the left. Choosing different Lyapunov candidates then just corresponds to moving this point around on our axes. However, not every point in 3D space corresponds to a Lyapunov candidate. When we stretch our ellipses out to straight lines, we get stuck, and there's a circular boundary that we can't push through. A more thorough exploration reveals that there's a surface that we can't get through. Every point inside this surface corresponds to a valid Lyapunov candidate, and the points on the boundary correspond to these degenerate cases that we can still use to verify instability but not stability. It's at this point our optimization friend bustles back into the room, declaring enthusiastically that we've decided to take his advice. Undeterred by our vacant expressions, he then goes on to explain that we've managed to represent our class of Lyapunov candidates using a cone. And this clarification has little impact. He then goes on to explain that a convex cone is a special type of set, in which if a point is in the set, then every point in a ray from the origin is also in the set. And also if 2 points are in the set, then every point along the straight line connecting those 2 points is also in the set. Though unable to fully match his enthusiasm, we couldn't help but notice when moving along the ray, the shape of our Lyapunov function didn't really change. The level sets moved in and out, but from the perspective of Lyapunov stability criterion and trapping in the trajectories of our system, these points are all equivalent. This means that when choosing a Lyapunov candidate from our set of Lyapunov candidates, we may as well just look along a single slice. To round things off, let's allow a freshly sheared version of myself to point us through the process of relating the search for Lyapunov functions to the identification of fixed points. We'll restrict ourselves to the case that our state space model is linear, meaning that the function f is simply just a matrix multiplied by the state vector. We're going to achieve this by creating a mapping from our circle of Lyapunov candidates back onto itself. By then continuously deforming this circle into a triangle, we can then guarantee that this mapping has a fixed point by Brouwer's fixed point theorem, and we'll use this fixed point to generate a Lyapunov function that will either demonstrate stability or instability of the state space model. We'll start by taking a leaf out of the control system engineer's book and write down the Lyapunov function that we want. So instead of demonstrating an inequality, we'll aim for an equality, but add in an extra term. As long as epsilon is bigger than 0, any Lyapunov candidate that we can find to satisfy this equation will also be a Lyapunov function. The next thing that we notice is that every term in this equation can be represented by a vector. The first term is simply the vector p corresponding to the Lyapunov candidate itself. Because our state space dynamics are linear, the second term is just a linear transformation of our Lyapunov candidate. When we were investigating Lyapunov candidates earlier, we found that this just corresponded to squishing and rotating other Lyapunov candidates. Let's call this vector q. It won't necessarily lie on our circle, but it must be somewhere within our cone. This final term is also a Lyapunov candidate. In fact, it's on exactly the same form as the very first Lyapunov candidate that we investigated. The sum of these two terms gives us another vector that must lie somewhere within our cone. By then rescaling this vector, we can project it back onto our circle. This generates a map from input points on our circle of Lyapunov candidates back to other points on our circle of Lyapunov candidates. Going through and labeling things up, we end up with a vector equation that's uncannily similar to our original equation. The only slight difference is that we have to introduce an extra term lambda that corresponds to the rescaling to get us back onto the circle. So how can we use this to generate a Lyapunov function? It's at this point in our story that our mathematician friend returns to remind us that we need only demonstrate existence. Brouwer's fixed point theorem guarantees that for every value of epsilon our mapping will have a fixed point. That fixed point will be associated with a particular value of lambda. Let's try to find one with a value of lambda less than 1 by creating a sequence generated by ever smaller values of epsilon. Suppose our first fixed point is here, and by halving epsilon, our second fixed point is here. Continuing this process, we can create an infinite list of solutions to our equation, each solution associated with a different value of lambda. By essentially rerunning our argument about a convergent subsequence of triangles from earlier on, we can conclude that this sequence of fixed points has a convergent subsequence. The point that this subsequence is converging towards corresponds to a solution to our equation, but with the value of epsilon set to 0. There are now two possibilities. The value of lambda that this limit point is associated with is either less than 1 or greater than or equal to 1. If it's greater than or equal to 1, we will have in fact generated a Lyapunov function that proves instability. If lambda is less than 1, it's not immediate that we can use the corresponding limit point as our Lyapunov function, because it might lie on the boundary of our circle. But a boring calculation reveals that if the point does lie on the boundary, just by giving it a small nudge back into the interior of the circle, we do end up with a valid Lyapunov function. And there you have it, a very brief introduction to stability theory, Lyapunov functions, Brouwer's fixed point theorem, and more. Everything we talked about today extends immediately, no matter how large the state dimension, and by using more exotic cones can also be applied to nonlinear state space models as well. There is, of course, much more to say on all of this, but I think that's more than enough for now. And all that remains is for me to say thank you for listening.